This is the high temperature superconductor laboratory, where the team are developing HTS magnets. These magnets are an integral part of our plan to build a tokamak capable of producing commercial fusion power.
For the last 3 years, we've been increasing the technology readiness of the HTS magnet technology. We've gone from just starting with very individual pieces of tape and testing the properties of the pieces of tape. And then we've moved on to testing cables, and then quite quickly on to testing small coils and magnets.
The HTS team starts off with tapes that come from various manufacturers across the world. And those HTS tapes, they have certain properties and they've been studied in detail by many labs around the world. For us, the challenge is to turn those tapes into magnets.
At the beginning of the HTS development programme, milestones were set for the team to achieve over their research period.
We're actually quite a lot ahead of schedule. We had a series of milestones which went, I think, 5, 10, 15, 20 Tesla, and we've actually now achieved all of those.
We should have achieved 20 Tesla by 2020. We've exceeded 20 Tesla already. We've done that because the coil constructions that we've come up with have exceeded our expectations. And the tape performance is actually better in wound coil form than the short sample tests would indicate. So most of the modelling data that we've based our original designs on were on short sample tests from other laboratories some time ago. And in fact, the actual tape that we've purchased has outperformed based on those tests.
I think one of the most exciting things that we've done with the team, pushing for higher magnetic fields. One of the ways that our success has been measured so far was in Teslas. The magnetic field on the conductor that we're testing, to be precise. That's been very exciting, just to see, look at the numbers, see it happen. That's, yeah, I think that's the most exciting bit.
We've demonstrated that the tape works at the magnetic fields and the current levels that we need and the temperatures, and now we need to scale up, and that means storing more magnetic energy, dealing with that magnetic energy if the coil quenches, and dealing with all the very large stresses and forces that come with a larger structure. So the idea is to have a very rapid development cycle of just testing ever bigger magnets. We have a plan scheduled out for the next year to do that, and we're moving now rapidly on to building a larger scale demonstrator magnet in the form of a small spherical tokamak, similar to ST25 but about 100 times higher in magnetic field.
The work of the HTS team has been instrumental in the design of STF1, our fusion power demonstrator, and in moving ahead with our plans of grid connectivity in the 2030s.
We've had the most fantastic team. You know, it started with just me and Greg. We're up to, I think, 10 people on HTS now. You know, my responsibility's moved on, so I've handed the HTS baton to Bateman. He'll be in charge of building the bigger device. But yeah, it's been a fantastic exercise in seeing a team grow and develop, and everybody's been pulling their weight. People have worked in, you know, on detailed technical models, and 1 minute and then the next minute they're down in the lab, you know, building the actual things. I think that's what's so exciting for a lot of people coming to work at Tokamak Energy, is that you get to take an idea from a complete concept that's hardly anyone's thought about, and very quickly you can be building, you know, a magnet based on your ideas. It either works or it blows up, but both of those results are good. The team's been brilliant, yeah.